Hello everyone. Welcome back to our Toronto AI Robotics L seminar. Today, we're glad to invite Joanne Truong from Georgia Tech to present her work on Sim2Robot, training robots for the real world with imperfect simulators. Joanne Truong is a fourth-year PhD student at Georgia Tech, co-advised by Professor Drew Bartroff and Professor Sonia Chernover. Her research lies at the intersection of machine learning and robotics, and generally focuses on pre-training AI agents for complex tasks in realistic simulators before transferring the skills learned to real robotic platforms. She is a recipient of the NSF Graduate Research Fellowship, Apple Scholars in AI/ML PhD Fellowship, Adobe Research Fellowship, and Google Women Tech Makers Scholarship. So yeah, John, we are all looking forward to your talk. The stage is yours.
Yeah, thank you so much for having me. So I'll just get right to it. So let's start. So I'd like to start by taking a look at how robots are being used now. So they're typically only used in very controlled environments such as factories, and they're programmed to execute the same precise movements repeatedly, for example, for an assembly task. And these robots don't need to interact with humans at all or need to find a way to deal with the messy real world that lies outside of this factory environment. But instead, the robots that we're all envisioning and hoping to bring to life are ones that can work in these complex real-world environments. And some applications of these robots include home assistant robots, healthcare robotics, or autonomous vehicles, just to name a few. And developing these robots is challenging since instead of working in controlled environments, like what we saw with factories, these robots now have to work in dynamic human-centered environments, and they might also need to interact with humans themselves. And this makes it very difficult for us to program these robots to work for every scenario possible, especially when the environment itself is so complex and unpredictable. So are we not there yet? We've seen many videos of robot successes through the years. So from 2012, we had quadcopters navigating through tight spaces. And more recently, we have videos from Boston Dynamics where their robots are doing parkour, they're jumping and they're flipping and they're interacting with their environment. However, I would argue that we're still not there. What these videos don't show us is a team of control engineers that make this possible. And designing these controllers is often very time-consuming and difficult to do. And despite taking the time to hand design these controllers can still fail when faced with corner cases in the real world that were not properly accounted for. So instead, many have turned towards learning-based approaches as an alternative to handcrafting robot controllers. And some popular techniques include imitation learning and reinforcement learning. And both of these have shown impressive results. And today I'll focus on reinforcement learning. So deep reinforcement learning is a very powerful method, but it is also very data hungry. And robot data in the real world is often very time-consuming and difficult to collect. So others have turned towards using simulators as a solution. Simulators allow us to study complex tasks such as locomotion, rearrangement or navigation, and also manipulation. And the benefits of simulators are that it's safe, so it allows researchers to study corner cases that might be challenging to recreate without damaging or causing wear and tear to the robotic platforms. Simulators are fast and scalable, so simulators can run orders of magnitude faster than real time and can be parallelized over a cluster, and this enables decades of experience to be collected in days. Simulators also enable fair comparison and benchmarking. With the AI community running challenge competitions, they're able to evaluate the models in identical settings, and this leads to more reproducible results. Simulators are cheap and it lowers the barrier to entry, especially for those who don't have access to real hardware. And simulators are also diverse in that it supports a variety of tasks and also data sets, allowing researchers to train and test in different scenarios. But one drawback about simulators is that no simulator is perfect. And we've actually seen that AI systems have learned to cheat by exploiting these imperfections in the simulator. So here is an example from a paper from OpenAI in which they want to train two agents to learn and play hide and seek. So we have the blue agents here who are the hiders and the red agents here who are the seekers. And the hiders have learned over time to build these shelters out of boxes in order to protect themselves from the seeker. So what the seeker has learned to do is actually, it's learned to surf on top of these boxes in order to reach the hider and in order to win the game. However, this is very unrealistic, and this is only possible due to a physics error in the simulator in which they allow the seeker to exert a force onto themselves regardless or not if they're on their floor. So because of this physics error, the seeker was able to exploit this and win the game. But obviously, this won't translate to the real world because this was learned in an imperfect simulator. And this is not just a one-off case. So this has happened within that same simulator itself again. So here, the seeker has learned that if it were to push the ramp at the wall at a very particular angle, it will actually launch itself and be able to catch the hiders again. In a different scenario, these researchers, they wanted to explore the possible interactions between this robot arm and the cube on the table. And so here the researchers purposely closed or disabled the gripper. They wanted to investigate the different ways that this robot arm could push this block around the table. But what the algorithm found was that if you hit the box with the gripper in just the right ways, you can actually force the gripper to open and hold the box. And so this effectively cheats by re-enabling the disabled gripper. And in one more example here, the authors wanted to experiment with learning a locomotion controller that would be robust to, for an example, damaged legs. So in this example, they wanted their controller to walk in the setting where one leg is damaged. And they slowly increased this number of legs that the robot had damaged. So here we see the case with 3 damaged legs and the robot is still able to walk. And for the sake of completeness, they tried all 6, expecting this to fail. But what they saw was that their algorithm learned to topple their robot over, and so that their robot ended up walking on their elbows. So this agent was able to cheat by walking on the robot's elbows. And I've only shown a couple examples, but there are many more instances of this happening. In fact, there was a researcher from DeepMind that compiled this master list of all the times that AI systems have cheated and undermined the researcher's original intent in the experiment when accomplishing its given task. So this brings about the question, how can we train robots in imperfect simulators while ensuring that the learned skills generalize to the real world? And today I'll argue that simulators need not be perfect. They don't need to model everything about the world, only what's necessary for generalization. And specifically, I'll show generalization across one, novel environments that are in distribution, such as training robots in simulated indoor environments and translating them to novel real-world indoor environments. And what's important here for generalization is sim-to-real predictivity. So simulators should be optimized to predict how well the models will perform in the real world. And also what's important is to close the sim-to-real gap, so adapting the visual and dynamics for both the simulator to match the real world, and to generalize to novel environments that are out of distribution, such as training in simulated indoor environments and translating them to novel real world and outdoor environments. What's important is environmental or context hints. So information that we have about the environment that us as humans can get freely, we should provide these to our robots as well to enable this generalization. So I'll be going over 4 main projects today, and I'll start by looking at how we can quantify sim-to-real predictivity. So a key question that we must first answer when relying on robots, simulation to pre-train robots is, does progress in simulation translate to progress on real robots? And concretely, if one method outperforms another in simulation, will it continue to do so when deployed on a robot in the real world? And this question is important to ask as more research has focused on developing simulators and more embodied AI challenges have been proposed, such as the Habitat Challenge, iGibson, AI2 Thor, or Alpha challenges, just to name a few. If all the research and challenge benchmarks are performed entirely in simulation, how can we know that we can actually trust that the outcomes of these challenges will hold true in the real world? So we'll examine this question in the task of point goal navigation. So in this task, the robot is initialized in a novel environment, and it needs to navigate from its starting location to a goal location, such as go to delta X or delta Y. And the robot has access to an egocentric RGBD observation and also an ego motion sensor that's used to calculate the goal location relative to the robot's current pose. And this top-down map is not visible to the robot, and it's only used for visualization. So for evaluation, we'll be primarily looking at success rate and also success weighted by path length, or SPL, which measures the robot's path efficiency. So first, to directly compare performance in simulation and in the real world, we first virtualized a real world lab environment that we had at Georgia Tech. So we placed a 3D scanner at various locations of our environment to collect 360 scans. And these scans are used to construct highly realistic 3D meshes of the environment. And these 3D meshes can be directly imported into the simulator. And this is a streamlined process that enables, that is scalable and enables quick virtualization of physical spaces. So the results of this is that we now have paired worlds. So we have the real world lab environment, and we also have a virtualized replica of the environment in simulation. We also have the same robots in both environments, which allows us to run paired experiments. So now we can run identical experiments using the same models in both simulation and the real world. And now we can see how the performance is different between the two. So we conducted a total of 810 parallel experiments across 3 room configurations. And what these experiments allowed us to do is we can run the model in the real world, and then we would freeze the results of the reality experiments. And then we can rerun the experiments in simulation, but this time we change the parameters of the simulator and we tune the parameters such as noise, and then we can examine the simulator's predictivity. And the simulator's predictivity is defined as how well does the performance in simulation correlates with the performance in the real world. And we want to maximize the simulator's sim-to-real predictivity, since a high predictivity would enable researchers to use simulation for evaluation with confidence that the performance of different models will generalize to real robots. So we proposed a new metric called Sim versus Real Correlation Coefficient, or SRCC for short. Here, the x-axis represents the robot's performance in simulation. The y-axis represents the robot's performance in reality. And if the data points lie in this bottom region, this indicates that the model performed better in simulation than in the real world. And if the data points are on this top region, then the model performed better in the real world than in simulation. What we want to see is points lying along this diagonal of the line, or to have an SRCC value close to 1, as this would indicate a high linear correlation between performance in simulation and reality. And SRCC is calculated as the sample Pearson correlation across the data points. So first, we study the SRCC using the simulators parameters from the 2019 AI Habitat Simulation Challenge. So we tested 9 different learning-based techniques, and we found that there was a low SRCC correlation. And this suggests that the results and winners may not be the same if the challenge were run in the real world. And if you look at this plot, you see that a majority of the models perform very well in simulation, so they have a near perfect success rate, but the performance degraded a lot when tested in the real world. And we discovered that a key factor that led to this low sim-to-real predictivity is due to a sliding behavior in the simulator. And this is the common behavior that's enabled by default in many simulators and video game engines that deploy a physics backend. So for an example, if you're playing a video game and if your character gets its shoulder caught along the side of a wall, instead of your character getting stuck on this wall, what would happen is that your character would actually be able to slide and move alongside this wall. And the sliding occurs because there's no perfect physics simulator, there are only approximations, and this type of physics allows for smooth human control, but does not accurately reflect real-world physics. On the other hand, with sliding disabled, the robot would get stuck on these obstacles and it needs to turn to break away from these obstacles. So specifically in simulation, how an agent can cheat is, for example, if you look at this top-down map where the white denotes an obstacle and the gray denotes a free space, if the agent is at state ST and wants to take a step forward, the simulator would first calculate the final location for this forward action. If the step were collision-free, it would then search for the next navigable location closest to this collision-free point within a constraint. And finally, the agent is moved to this newfound location, effectively sliding it around obstacles if necessary. And this leads to a higher SPL metric, since the simulator would calculate the agent's path length as 0.28 meters instead of the 0.43 meters that it actually traveled. And of course, this is incredibly unrealistic, since a real robot can never cheat in this way, but this behavior actually went unnoticed for a very long time, since this was such a standard way to implement simulators. But what we found was that RL agents were able to find and exploit this imperfection in the simulator and was able to cheat to get high performance. And therefore, when the agents were evaluated in the real world, it would try to drive towards an obstacle or a wall with the expectation that it would also be able to slide around the corner, which of course would not happen in the real world. So to prevent agents from cheating in simulation, we modify Habitat to disable sliding on collision, and we search over simulation parameters to optimize for SRCC. And after this optimization, we now see an improvement in the SRCC value, and we also see a better alignment in the success SRCC scatter plot. And this improved sim-to-real predictivity. It increases confidence that in simulation comparisons will translate to real robots. And also it provides for a formal approach to simulator design instead of operating on intuitions and qualitative assessments. So from these results, the subsequent challenges proposed in the Embodied AI workshop at CVPR 2020 and 2021 have focused on realism and sim-to-real predictivity by disabling sliding, adding realistic sensor noises, and also by directly evaluating robot policies in the real world. So some takeaways of this is that SRCC optimization reveals simulation parameters that allow agents to cheat. Sim-to-real predictivity enables researchers to use simulation for evaluation with confidence that the performance of different models will generalize to the real robots. But some limitations of this approach are that SRCC is measured based on a population of methods. So that depending on the methods that you tested, the SRCC values may be different. For our experiments, we ran this using the methods from the 2019 AI Habitat Challenge, but there's been a lot of progress made since then, so it's important to rerun this with the new methods that have come out since. So now that we can use simulators to predict, oh yes.
Sorry to interrupt. Yeah, so this is very great work and I really appreciate the effort here, but I have a question. So here you're only showing one simulation and real world environment pair, right? I'm just curious, does this observation hold on other pairs? Because for just one environment, probably there are some randomness here, right, among different methods. Did you try other paired environment, and does this observation also hold in different environments?
Yeah, so we were specifically doing this using the models from the AI Habitat Challenge. So that is just using one simulator. And we were trying to find out what parameters of this specific simulator would lead to AI agents cheating. But this can be repeated for different simulators as well to see how the simulator may be imperfect. And RL agents are really good at finding the ways that these simulators are imperfect. So we haven't tried it for this particular paper across simulators and across scenes, but in my other works, I do use different simulators and I do investigate like the sim-to-real gap across different simulators as well. And yeah, in my last work, I'll also show how we can do sim-to-real with environments that are also hard to model. So in this case, we only test in this one environment because we were able to scan it at Georgia Tech. But in my last work, I'll show how we can show sim-to-real in environments that are difficult to scan as well.
Sure, thanks.
Yeah, thank you for the question. Yeah, so from the first work, we can use simulation to predict results in the real world, but these simulators are still imperfect and they fail to model many aspects of the robot and the environment. So to combat this, we'll look at two methods for closing the sim-to-real gap. So I'll talk about the first project, which aims to close both the visual and dynamics sim-to-real gap. So first, I'll reframe the sim-to-real transfer problem as given a cheap, abundant, low-fidelity data generator, so a simulator, and an expensive, scarce, high-fidelity data source, or the real world, how should we best leverage the two to maximize performance of a model in the real world? And we argue that the small amount of expensive, high-fidelity data from the real world is better utilized to adapt the simulator rather than to adapt the policy itself. So prior works have investigated domain adaptation techniques for adapting vision-based models to translate images from sim to real during training for manipulation tasks, and other works have focused on adapting policies for dynamic changes. But in our work, Bi-directional domain adaptation, or BDA for short, our work produces the sim to real gap for both the visual and dynamics domain in two directions. So we do sim to real for the dynamics gap, and we do real to sim for the visual gap. So starting from sim to real, given a robot in simulation at state ST sim and observation IT sim, the robot will take an action AT to reach the next state ST+1 sim. We learn a sim to real dynamics adaptation module to predict the residual error between the robot state transitions in simulation and reality. And specifically, this dynamics adaptation module is a 3-layer neural network that takes as input the robot's position and orientation, and also the action taken by the robot. And the output is the estimated change in position between the two state transitions. And data to train this domain adapter was collected using real-world rollouts from a behavior policy PySim. And once trained, this dynamics adaptation module is used to directly augment the simulator to expose the robot to trajectories expected in the real world. And our hypothesis is that using real-world data to adapt the simulator with our dynamics adaptation module will pay off, because then we can train RL policies in this augmented simulator for large amounts of experience cheaply. And now, next we adapt from real to sim. So given a robot in the real world at state ST real and observation IT real, We learn a real-to-sim observation adaptation module and use it at test time to make real observations look like the ones seen during training and simulation. So specifically, we leverage CycleGAN, which enables pixel-level image-to-image translation with unpaired images as our observation adapter. And this ability to learn mappings from unpaired images from both domains is important because it's difficult to accurately collect paired images between simulation and the real world. So here's an example of the translation. So on the left, you have an image from this simulator. In the middle, you have a noisy image in the target environment. And then the right, we have an image that shows the generated we have an image that's generated after applying our observation adapter. And if we were to zoom in here, we see that the image on the right now looks similar to the image on the left. And after applying these observation adaptation module, the robot can then take an action AT to reach the next state as T+1 real. And this bidirectional formulation allows us to exploit the differences between simulation and reality. So Sim2Real dynamics adaptation nicely exploits the fundamental asymmetry between the two domains. So simulators can typically be reset to arbitrary states, whereas the reality cannot. And so by augmenting our simulator with this Sim2Real dynamics adaptation module, we can reset the states of our agents in simulation to train a policy using states expected in the real world. And once trained, this policy can be deployed in the real world with the robot augmented with the real-to-sim observation adaptation module. And this real-to-sim observation adaptation module decouples sensing and acting. So if the sensor characteristics in the real world change, but the dynamics stay the same, for an example, the same robot, but a different camera, this policy doesn't need to be retrained, but it only needs to be equipped with a retrained observation adapter. So to summarize, the core strengths are that BDA decouples sensing and acting. It doesn't require paired training data, and data to train both modules can be collected jointly, but the two can be trained in parallel independently of each other. So we use sim-to-sim transfer as a standard for sim-to-real transfer due to our limitations in our ability to collect reality experiments. This was during the peak of the pandemic, so I wasn't able to run real-world experiments for this paper. And our source simulator is a typical simulation environment in which RGBD sensors and the dynamics do not contain any noise. And our target simulator is a simulator augmented with observation noise that's characterized by real-world prime-sense cameras, and the dynamics noise is obtained via mocap data on a real-world locobot. And we use this to mimic noise observed in the real robot. So first, we aim to investigate how large the sim-to-real gap is. So to do so, we train point goal navigation policies in the habitat simulator using the Gibson dataset. And we use DDPPO for training, which is a decentralized distributed variant of the proximal policy algorithm. And our policy is composed of a ResNet50 visual encoder and a 2-layer LSTM that was trained to 100 million steps to ensure convergence. We test the policies that were trained in a held out lab environment with 4 different noise settings. So this column represents the lab environment without any noise present. This is the lab environment with observation noise, with dynamics noise, and with both observation and dynamics noise. So first, we train a policy in an environment without any noise present, and we see that this policy transfers well to the lab environment that similarly does not have any noise present. However, when we introduce dynamics noise, we notice a 28% drop in performance. And more importantly, we see an 80% drop in performance in the environment with observation noise, and similarly, a 78% drop in performance in the environment with observation and dynamics noise. So from these experiments, we see that in the absence of noise, generalization across scenes, so from Gibson to the lab environment is good, but in the presence of noise, the generalization suffers. And we also study the performance of a policy that's trained directly in the target environment, which contains observation and dynamics noise. From these experiments, we also noticed that the converse is true. So the policy that was trained directly in the target environment with both observation and dynamics noise performs well in the lab environment with observation and dynamics noise, but the policy fails to generalize the lab environments with no observation and dynamics noise present. And this shows that RL agents are highly sensitive to what might be considered perceptually minor changes to visual input. So next, we investigate the performance of a policy that's fine-tuned for 1 million steps directly in the target environment. And we compare that to our method, which utilizes the observation and dynamics adaptation modules that were trained using 5,000 examples from the target environment. We see that both policies are able to retain performance in all 4 variants of the lab environment. And additionally, we see that our method performs comparably to the policy that was trained directly in the target environment for 1 million samples, while our approach uses 200 times less data. And finally, we investigate the sample efficiency of our model. So we retrain our observation and dynamics adaptation modules using varying amounts of data collected in the target environment with up to 5,000 samples. And we reevaluate the performance. So the x-axis here represents the number of samples collected in the target environment, as well as an approximation for the time needed to collect the data in the real world. And the y-axis shows the performance in the evaluation environment. And we see that the majority of our success comes from the first 1,000 samples in the target environment, and that we're able to match the performance of a policy fine-tuned directly in the target environment 117 times faster. And this result gives us confidence in the importance of our approach as we wish to limit the amount of data needed from a target environment. So in conclusion, this work leverages the differences between simulation and reality to accelerate learning and improve generalization of RL policies. We use real-to-sim adaptation to close the visual domain gap and sim-to-real adaptation to close the dynamics domain gap. And we find that reducing the sim-to-real gap with BDA is much more sample efficient than fine-tuning a policy directly in the target environment. So next, we'll build on this and see how we can close the sim-to-real gap for robots with more complex dynamics, such as quadrupeds. So we've established that no simulator is a perfect replica of reality, but the default hypothesis is that increasing simulator fidelity would reduce the sim-to-real gap. In our work, we question this and we ask, can sim-to-real transfer be improved by decreasing simulation fidelity? So to investigate this, we study this for navigation again, and we use 2 levels of physics fidelities when training our robots. We use kinematic and dynamic. Kinematic simulation uses abstracted physics, and it teleports the robot to the next state using Euler integration. And kinematic policies command center of mass, linear, and angular velocities. And then we also compare this against dynamic simulation, which consists of rigid body mechanics, and this simulates contact dynamics. Dynamic policies command center of mass, linear, and angular velocities, which are then converted to robot joint torques by a low-level controller that's operating at 240 Hertz. We evaluate this in a novel lab environment where each policy is tested for 5 different episodes in the real world, and we report the average over the 3 trials. And this is an example of the 5 different episodes in the real world. And we find that all kinematic policies achieve 100% success rate. And additionally, the kinematic policies that were trained in Habitat take on average 26.4 actions and collide on average 3.1 times. In comparison, policies that were trained dynamically have a success rate of 40 to 67%, depending on the simulator used to train it. And on average, the dynamic policies took 107 actions and collided 41 times. And we also evaluate this in simulation across 3 different robots, 2 simulators, and 2 physics fidelities. So we use Spot, A1, and Alien Go. We do this across Habitat and Gibson. And we also investigate, again, kinematic and dynamic physics fidelities. We first ask the question, how large is the sim-to-sim gap? And we find that it's high for dynamic policies and low for kinematic policies. So we study the combinatorial space of experience. So we have policies that are trained under 2 conditions, so kinematic and dynamic. We evaluate this also under kinematic and dynamic conditions. We study this across the 2 simulators, Habitat and Gibson, and across 3 robots, so Alien Go, Spot, and A1. And if we look at the kinematically trained policies in the left column, we see that they outperform the dynamically trained policies in the right column in terms of success rate. And this holds true even when the kinematic policies are evaluated in the dynamic environment. So this is evaluating out of distribution as shown in the lower left-hand quadrant. And we find that this holds true for all 3 robots as well. And so we plot the evaluation performance of both the policies in kinematic and dynamic simulation. And we find that the kinematic trained policies outperform the dynamic ones because of the scale at which it can train at. So both policies are trained to convergence, so 3 days for the kinematic policies and 7 days for the dynamic policies, both using the same compute. And we see that kinematic training leads to a 12% increase in success rate compared to the policies trained dynamically. And again, this plot shows the kinematic trained policies that are evaluated dynamically. So the kinematic ones are being evaluated out of distribution here. And this is investigating the wall clock time. But if we look at the plot for the steps of experience, we see that kinematic training is much faster than training dynamically. So with kinematic training, the robot is able to learn from approximately 10 times more experience than with dynamic training, despite training for less wall clock time. And this increased experience is crucial for end-to-end learned approaches and allows the kinematic policies to learn this intelligent high-level reasoning. So some takeaways from this are that higher fidelity simulation does not necessarily result in higher sim-to-real transfer for navigation. And we find that the benefits of low fidelity simulation are that it leads to faster simulation, which enables more experience to be collected, which enables robustness to dynamics in the real world. And we also don't need to implement these low-level controllers in simulation, which ends up saving the developer time. In contrast, the dynamic policies overfit to the physics in simulation, and they don't generalize well to the real world. So our takeaway from this is that we should invest in simulation speed and not physics fidelity if there's a trade-off between the two. So lastly, I'll talk about how we can build on these advancements for from indoor visual navigation and leverage simulators to enable sim-to-real out of lab environments and into the wild. So our approach is called indoor sim to outdoor real, and this enables a quadrupedal robot to successfully navigate hundreds of meters in novel outdoor environments around previously unseen outdoor obstacles such as bushes, slope grounds, and cars. And this work, again, leverages advancements made in indoor visual navigation, where we train the robot solely in simulated indoor environments using short-range trajectories, and we zero-shot transfer to the outdoors for long-range navigation using the Spot robot. So taking a step back, there's been a long history of outdoor navigation for both wheeled robots, autonomous vehicles, and also legged robots. And these approaches have all demonstrated successful long-range outdoor navigation. However, these prior works typically leverage large offline data sets that are collected through hours of human teleoperation, or they rely on classical planning methods that leverage accurately pre-computed maps, or they leverage waypoints from map services such as Google Maps. In contrast, our work leverages approximate or inaccurate maps. Our method is learned entirely in simulation and transfers to the real world zero shot. And we also use no real world experience, either indoor or outdoor. So again, we focus on the task of point goal navigation, and we train our policy using the habitat simulator. We use a large scale data sets of photorealistic 3D scans of indoor environments. So specifically, we use the HM3D and iGibson data sets. And we first train a navigation policy. And this policy operates solely using the GPS and compass sensor, which is used to calculate a goal vector, and then also the depth observations. In simulation, we find that these policies are able to navigate short ranges to successfully reach the goal. And so we first wanted to see what would happen if we were to directly transfer this policy to the real robot. So we call this policy the no context policy, and we task the robot with navigating 38 meters forward and 16 meters to the right. And since the goal vector indicates that the goal is towards the right, the robot starts walking towards the right and it makes a beeline towards the goal. However, this results in the policy getting stuck around the obstacles and it ends up failing the episode. So therefore, to enable this long-range navigation, we want to leverage additional context information such as satellite maps that are freely available outdoors through public map services to enable long-range navigation. And we provide the policy with this context in the form of a rough sketch of a map by a human. In our work, we call these maps context maps. And context maps are an occupancy map with the white representing free space and black representing obstacles. And if we were to overlay these context maps on top of the satellite image, we see that these maps are inaccurate and outdated. For an example, the context map is missing large portions of the building or details such as cars, peoples, and bushes. But crucially, this map conveys a hint for the path to the goal. So we train a policy to utilize additional context input, and this context can be in the form of this map or ground truth trajectory or ground truth waypoints for the robot to follow. These context inputs are encoded into context features, and we compute the scale dot product attention between the depth and context features. These attended features are then passed into a second GRU, and note that we're not running any planning algorithms on the map. They're simply being fed in as an additional policy to a learned, additional input to a learned policy. So we train this policy entirely in simulation using ground truth maps that we get for free from simulated indoor environments. And to deploy the policy to the real world, a human operator would sketch a context map that's fed into the policy. So this middle map that you see here. And for an example, this map was drawn by me using preview on a Mac computer. But you can also automatically generate these images from a digital map by segmenting out either roads or buildings, or you can imagine a human operator using an iPad to sketch out a map for the robot. And we test zero-shot sim-to-real indoor to outdoor transfer for our context map policies. And this robot has access to an ego motion sensor, the depth observations from Spot's front cameras, and the inaccurate context map. In all tests, the Boston Dynamics obstacle avoidance API is disabled. And here we're tasking the robot with navigating to a long-range goal outdoors with many real-world obstacles present, such as bushes, tables, chairs, and pedestrians. And we find that the robot is able to reach the goal successfully. The policy is able to leverage the context maps to bias its search during outdoor navigation, and it's able to reach the distant goal location 100% of the time without a single collision or human intervention. And we also find that the robot learns to use these inaccurate maps in conjunction with observations from its onboard cameras to adapt to the on-the-ground reality. So it's able to avoid obstacles that are not drawn on the map, such as bushes, chairs, people, and it's able to navigate in various terrains, including dirt slopes and grass. We also investigate applying traditional planning methods directly on these outdated context maps as a baseline. So we run our T-star on this inaccurate context map to extract waypoints to the goal. And again, this is the exact same map that was used for our context map policy that was able to successfully reach that distant goal. So these waypoints are directly used with the context waypoint policy, which was trained in simulation to follow waypoints to the goal. And we see that this policy is able to successfully navigate to each successive waypoint. But because the waypoints were generated from an outdated map, the robot ended up missing the actual opening in the bushes. And this confirms our conjecture that these classical planning-based approaches are highly sensitive to the map input, and they're not able to adapt to the gross inaccuracies present in the maps. So in the real world, creating a perfect, complete, and always up-to-date map is not realistic. And therefore, we see that traditional planning methods on these outdated maps ends up failing the episode. We additionally test the robustness of our policy by adding varying degrees of noise to our context maps in simulation. So in this 100% noise scenario, the robot is given a map where everything is denoted as free space. We also use shift noise, which randomly shifts the map provided to the robot in any direction. And this simulates localization errors that may occur on the robot. We also additionally use cutout noise, which randomly adds patches of free space or obstacle space to the map. And this simulates giving the robot an outdated map, for an example, a map with missing or additional obstacles in the environment. So first, we see that in simulation, the use of context maps improves performance by 16.7%. And when adding noise to the environment, we find that our policies that were trained entirely using perfect maps are surprisingly robust to these noisy maps. So at 50% noise, the original top-down map is barely visible, and planning algorithms would be unable to find any feasible path to the goal. But in contrast, our policy is still able to navigate to the goal successfully 81.4% of the time. And we see that at 100% noise, the context map policy behavior gracefully regresses to the no context policy behavior, which exhibits the best of both worlds. So it's able to utilize the information in the map when it's available, but it never underperforms the map-free approach. So some takeaways from this are that context maps enable zero-shot sim-to-real transfer to the outdoors for long-range navigation, and simulators can be used for real-world transfer without having to a priori design and model the deployment scenario. So today we've shown that imperfect simulators can be a very powerful tool for us to pre-train robots and teach robots to perform complex tasks that can be transferred to real robotic platforms. Additionally, we've shown that data collected in the real world can be used to improve simulators and help develop RL agents that are more robust to small changes in the environment, and that these policies can be transferred to environments that are hard to model, such as the outdoors. And I believe that a close integration between both simulation and the real world is crucial towards developing the intelligent robots that we're all envisioning. So while simulators can be leveraged to train good initial policies, the robots must also be able to continually update its policy and adapt as our real world is fast-paced and constantly changing. So instead of keeping robot learning into a training and deployment stage, where the learned policies are kept fixed in the real world, I believe that the future of robotics lies in developing methods that allow for this lifelong learning in the real world. And with that, I'd like to thank my collaborators and thank you all for listening. And I'll end on this slide and open up the floor for questions.
Yeah, thanks, John, for this wonderful talk. And it's our QA section now. If you have any questions, just unmute yourself and ask.
Yeah, thanks so much. It's really a super interesting talk, and like we're also super excited about simulation. I have a few general questions. So first of all, what are your thoughts about mapless navigation in general? So for example, I also have worked a little bit on it, and somehow like I feel like mapping systems became so good. So I sometimes start worrying like whether my work on mapless navigation will ever become like relevant, except for like very constrained environments, like even indoors or particularly indoors. Indoors is actually a very friendly environment because people's houses are very cluttered, and clutter is good for distinctiveness. I sometimes wonder, do you think this will become relevant? I still think it's interesting, and again, I also worked on it like for robot learning. But yeah, sometimes I have this concern to what extent it will be used.
Thank you for the question. This is actually a very relevant question since it's the next project that I hope to work on. So I think that in order to build robots that can work in a persistent environment or to ultimately be these robot assistants that help out in our everyday lives, these robots need memory of their environment, and a natural way for this memory to be given to these robots is in the form of a map. However, the way that this map is formulated may differ. So I believe in implicit maps. So I want to build like a neural spatial temporal implicit map for these robots to learn from as it's navigating through an environment over time. I believe that like 2D maps or voxel maps are not scalable enough to use in our real world. So in my next project, I hope to investigate using these implicit maps to aid in navigation over time. And I think that an interesting task that's been recently proposed in CVPR to tackle this is called iterative vision and language navigation, where they sort of have a spin on the traditional VLN task, in which they have the robot navigating over an environment over multiple episodes. And so throughout the episodes, the robot has some memory of where it's been before, and it can leverage this memory to aid in its future episodes.
Yeah, I agree. Like I think particularly for tasks which are like such as pick up my keys, the robot should maybe remember where the keys were. For the actual localization part, I feel like it's like the one part in localization that is difficult is actually office buildings that are very uniform, where the one floor looks almost the same as the next, except for the numbers and the office doors. So this is the one where current mapping systems have a hard time, and where also other mapping systems would have a hard time. They just need to teach them to read the door signs basically and use them for localization. But indoors, I think if you want to build like a general helper robot, you need memory, and the purpose of the memory is mainly to simply know about the non-persistent object, because everything that is persistent can go in a map. Like that's actually what the vacuum cleaners try to predict a map. It will. You're absolutely right. It will not be like a voxel-based map, because those voxel-based maps are not necessarily the most efficient. But what we were working on a long time ago, and what I think is now the default for mapping indoors, are like visual sparse key point maps. And these sparse key point maps, they are somewhat data efficient because they don't store everything everywhere. You just need to have like landmarks in the environment that you can recognize, and then an image retrieval task basically will help you with localization. But yeah, I agree, like the moment you want to do like reasoning about things that move around, there is no way around using some form of memory, right? And, yeah, so it's very, very interesting. It's also very interesting because a lot of these tasks basically, but what I think is cool, they are like, you can do a lot of research on these tasks without a robot because there are all these nice environments. And although I really like robots, like particularly your experiment with the Sim2Real, it's like a super cool experiment. But for some of the research, the robot was not necessary. Like you can deploy So it's like really good to have these very realistic environments that you can use, even though they are not realistic enough. That's a little bit my second question. What are your thoughts on realism? Like, so in Toronto, particularly Raquel's group, also my group, and in some sense also what Sanya and Florian is doing, there is this push to use simulators that are based on real world data. For physics, I guess it's hard, but even in physics, there's research on learned simulators, right? So how far can we push the simulators so that sim-to-real transfer will become less of a problem? Like, is your feeling we can make them realistic enough, or is there some basic limitation that we will always have?
Yeah, that's a great question. I think that our current limitation is in the compute. So I feel like there's always a talk of simulator fidelity and also simulator speed. So there's a trade-off between the two, and that we have to balance this. And this is why we have to do some tuning in the real world or adaptation, or have to sacrifice some fidelity in order to increase simulation speed. So I think that as simulators improve over time and compute gets better over time, there will become more realistic simulators that allow us to explore other tasks such as deformables and things that are prohibitively slow in simulation right now. And that's why most people just aim to learn directly from the real world. But I think that simulators can become more realistic over time, and then hopefully there will be a more seamless sim-to-real transfer then. But I think right now the compute is our bottleneck.
Yeah. Okay, yeah, I want to give some other people also question opportunity.
So, hi, thanks for the great talk. So I've been reading some sim-to-real transfer paper in the past, but most of them are about manipulation tasks. So I wonder, like, in your opinion, from the high level, what is the biggest difference between like a locomotion or navigation task and the manipulation? Like, do they have different like difficulties and different focuses in each task? Do you have any like sorts on that?
Yeah, so when you're talking about manipulation, I think there's also a wide spectrum there. So for manipulation, there can be like very dexterous manipulation, which is also hard to simulate in simulators. Or if you're just talking about roughly like picking and placing objects, that has also.
I guess I'm talking about I read both of them, and like probably, as you said, pick and place is relatively easier to simulate, but the dexterous simulation is harder. And also because in manipulation, you might encounter some like deformable objects and some physical phenomena that are very hard to simulate. Yeah, probably just compare with the harder one, I guess.
Wait, sorry, can you repeat your question one more time?
Yeah, like what are the like difference between these two types of sim-to-real transfer in your opinion? Like I guess because navigation is like a large scale or relatively larger scale task, but for manipulation it's usually just tabletop, right? But probably the challenge are different because in manipulation you need, I don't know, like low-level policy, and the objects you want to simulate, if they are deformable, then there are huge sim-to-real gap, I guess. But in navigation, from my understanding, the locomotion, the policies about locomotion, like moving, is probably slightly easier than manipulation. But because it's usually a larger scale environment, right? So there are different challenges here. I'm not sure if I'm correct, but this is my intuition about the two tasks. And I'm just wondering, how do you think about this?
Yeah, so I think that there are a lot of different simulators out there. And so depending on what task you want to do, you can leverage these simulators differently. So if you want to do more contact-rich tasks such as locomotion or manipulation, it's important to leverage these simulators such as Isaac Sim, which allow for more accurate physics at a very fast pace, but at the cost of not being able to render images. So if you're interested in locomotion, like blind locomotion or dexterous manipulation, then you can leverage those simulators. For other simulators like Habitat, which focus on this realistic or photorealistic rendering, this makes sense for tasks such as navigation or mobile manipulation, or like rough pick and place mobile manipulation. And some of my prior works have also investigated combining these two. So we trained a low-level controller in Isaac Sim that was blind, and we coupled that with a vision-based module navigation policy that was trained in Habitat. And we saw that we were able to directly connect these two, zero shot, and be able to enable locomotion where the robot has to like navigate over obstacles. So it has to use vision in order to learn how to step over obstacles. So it's fine-grained control, but it's still leveraging vision. And so we're able to take the benefits of each simulator in order to enable this. I don't know if that fully answers your question, but I think it depends on what input you want and what and how fast and accurate these simulators are able to provide you with the information you need.
Yeah, I see. So like in your third project, you mentioned that sometimes physical fidelity is not like the best thing we want. Sometimes like having a less realistic simulator, but if you can see more training data and train longer, that sometimes can lead to a better solution. And is that, did you only observe that in like navigation tasks, or do you feel like that will also generalize to like manipulation tasks?
So I can speak about this in terms of, again, that pick and place manipulation task, since one of my lab mates recently put out a paper that does this manipulation task. So what we've observed is that in order to have this really robust policy in the real world, it's very important for the robot to see a diverse amount of environments. So the vision here is what's and so because we're using vision for our policies, that's where sort of the diversity in environments and experience matters a lot. If you're learning like locomotion, where the vision doesn't matter and you can simulate accurate physics very fast, for an example, using Isaac Sim, then that's when sort of the physics fidelity plays a bigger factor. But again, you also have more, in that simulator, you have faster simulation speeds alongside it. So in our work, the limitation was really the rendering plus physics fidelity in terms of speed.
So what is the takeaway from that project? I'm just curious. From the
takeaway from,
yeah.
Sorry, can you repeat that?
Yeah, like the takeaway from that the recent project from your lab mate, the pick and place one. Do you observe that again? Like diversity is very important, so sometimes we can sacrifice the physical fidelity a little bit. Is that it?
Yeah, so in that work, he does mobile manipulation with the spot robot. The project is called Adaptive Skill Coordination. And in that project, they also use kinematic physics for the low-level control. So for navigation, you don't need to simulate this sort of low-level physics, and also for manipulation, it was also, you don't need to simulate the robot actually going and grasping it. We can just rely on these robust low-level controllers that are developed, such as from Boston Dynamics, in order to execute that grasp action. So if you can sort of abstract away the low-level control to these hand or expert design controllers, then we can enable faster simulation and lead to more robust policies.
Yep, that makes sense. Thanks. Any other questions? Okay, I guess if there's no more questions, we can thank Joanne again for this wonderful talk. And I'll end the recording, and thanks everyone for joining. See you next time.